Okay, so the SPEXOne instrument is a CubeSat-size polarimeter that's already mounted on the PACE Observatory. And I'm giving this presentation on behalf of Otto Hasekamp and his colleagues at ESRON in the Netherlands. I'm not sure whether you should visit the Netherlands in August or not, because it seems like there are no Dutch people there. They're all in Spain and France. So here's the science case. Lorraine's been talking about this. Aerosols are a big deal for atmospheric science. They are what water droplets nucleate on. They are also what ice particles nucleate on. And so the fact that we have clouds is entirely due to the fact that we have aerosol particles. And the aerosols do a good deal of scattering and absorption themselves. Here are the classic laundry list: soot, sulfate, dust, salt, pollen, biomass, a crystalline bioorganic, and then a marine organic. So there's a lot of shapes and sizes going on. There's a lot of pollution at the surface. And so aerosol remote sensing is something that's of great importance for understanding how our climate has and will change. There are sources that are mechanical. So bigger particles are generally formed from mechanical processes like sea salt caused by droplet impacts, and dust where you have saltation of the dust. And then there's emissions from smokestacks and volcanoes where oftentimes it's secondary particles, where the particles form from gases. We can't watch this very long because we have to be done by 5. Okay. So that's, I think, do you show this as well, Jeremy, at some point?
No, actually, take your time with it. It's a great video.
Okay, well, we'll let it run for a minute then. So this is a really nice simulation from the Goddard aerosol model. You see all the sea salt here. You see dust. This is probably smoke from, could be smoke, could be pollution. Where are we? Sulfates. Okay, so it's sulfates. And then they've got the organics, both in Amazonia and also from Central Africa. The biomass burning here season there is August through October. And so you see that going through. And then obviously there are also sulfates. This is probably fires in Borneo from forming that green. So a lot of stuff going on. Which reminds me, Lorraine made the good point that aerosols have been helping to keep the planet cool, which was beneficial. It's not something that you really want to be doing, though, as a matter of planning, because the time scale for aerosols to come out of the atmosphere is on the order of a week. The time scale for carbon dioxide to be removed from the atmosphere is on the order of centuries. So it's a Faustian bargain to try and use aerosols to solve the problem of carbon dioxide in the atmosphere. Although it was nice that they kept things a little bit cool for a while. This is just showing the Earth's energy budget. This is the reflected by clouds in the atmosphere, so 77 watts per meter squared. That's quite a bit. Part of the absorption is also aerosols. And actually, in terms of just the radiation budget of the Earth, the most uncertain one is actually back radiation, because satellites aren't, particularly passive satellites, really aren't very good at doing cloud base height. And cloud base height drives a lot of this back radiation. This is a cartoon of all the different things aerosols can do. They can do a lot. Primarily, they change the size of droplets. When you change the size of droplets, you can change the amount of air that you entrain at the top of a cloud. That can change the lifetime of the cloud. The size also changes the lifetime. And the size also changes how much reflection you can get out of the cloud. And as a result of that, the impact of aerosols, they have a big negative effect. They also have a big error bar. And I think it's fair to say that while this is, I think this is from IPCC, I think most people who have looked at the literature would probably say that this error bar is underestimated. And this error bar is overestimated. We really know what's happening with well-mixed greenhouse gases really, really well. What's happening with aerosols, their interactions with clouds, and the feedbacks on climate are really not known nearly as well. And the big kicker on all this, of course, is that because we haven't really known the aerosol forcing over the last 100 years, we have the climate sensitivity is the change in temperature divided by the total forcing. And since we don't know how negative the aerosol forcing was, the observations that we have over the last century of the Earth aren't that great in constraining climate sensitivity. We get better constraints out of paleo observations than we do out of the observations over the last century, primarily because of this. So, as I pointed out in the previous talk, it's all about taking microphysical properties when you're doing the remote sensing of aerosols, size distribution, shape, composition, go through the optics to simulate what the Earth's going to look like if you put that kind of aerosol, surface, ocean together in a radiative model. And so this slide's just reiterating brighter, how much brighter are clouds. Cloud modelers really detest the notion that aerosols make clouds live longer because cloud lifetime is sort of it's not really a thing at all. You can talk about the speed of a cloud life cycle, but talking about changing cloud lifetime, they really don't like that for some reason. The balance between scattering and absorption of solar radiation by aerosols, there was a good paper, probably almost 10 years ago now, looking at how well AeroNet could be used to constrain climate models and how much absorption there was by aerosols. And really the limit was the AeroNet sampling and also the way in which AeroNet just apportioned absorption to both the fine and the coarse mode of the aerosol, no matter what was happening, which then the models have to do something with, and they're not quite sure what to do with. So improvements in sampling and also in partitioning absorption between fine mode aerosols and coarse mode aerosols is really helpful in understanding the balance between scattering and absorption, both to understand the forcing better and also to understand whether models are simulating it well, so that we can do forecasts that have some validity and skill in forecasting. And as for pre-industrial aerosol properties, yeah, I mean, we really don't know what those were. So this is the about SPEXOne. You've seen cartoons very much like this. And one of the points of this, of course, is as I was pointing out, you have the phase function varying. You also have the degree of linear polarization associated with dust versus biomass burning looking very different. Biomass burning looks very much akin to molecular scattering, right? You have a peak in polarization right around 90 degrees. This is small particles. This is big particles. They look very different. And ideally, you want to have multiple angles to look at them so you can differentiate the phase function as well as getting the compositional information. So Polder 3 kicked off around 2005, and that was on Aerosol satellite and was in the A-train. So there's a really nice record from that instrument going through 2013, where you have Calliope, Modus Aqua, Parasol, all these different instruments. And so that's been a great source of information for developing new algorithms and looking at what you can do in combining instruments like Polder with Calliope. And now we're going to be having SPEXOne and HARP2 on pace. And then shortly thereafter, there'll be 3MI on the UMETSAT at 9:30 a.m. crossing satellites for probably about 20 years. So there'll be a lot of polarimeters flying around in space. And then there's the European CO2 mission that's been funded, and that's also going to have a multi-angle polarimeter, because in order to do CO2 at the accuracy that they need to correct the spectroscopy for the impacts of aerosols in the lines in the CO2 absorption spectrum. And so this is just, this is quite a nice cartoon actually. There we go. This is the instrument concept that they came up with. And these are some of the pieces that go into it. This is the polarization analysis piece of it. And then they built a ground-based instrument called, obviously, ground specs. And then they had a nice little thing that you could put on an iPhone 4S and do citizen science and do aerosols with this little specs instrument on your phone and try and do aerosol optical depth with an iPhone. And then they built Specs Airborne, and we did a campaign in 2017 with Van der Leyen and Lorraine and the group from UMBC had their air harp on the NASA ER2. There was my instrument, there were a couple of LiDARs, and that's been a great data set again for looking at how do we do remote sensing with the PACE payload, given that we've not had it on a satellite before. So we have these really nice airborne data sets that we've been using. And then eventually SPEXOne will be in orbit. And so this is Otto's summary. So Lorraine's going to talk all about HARP2 tomorrow, so I'm just going to only talk specs. So they have just 5 view angles, which is good for aerosol remote sensing. It doesn't really allow you to do the sort of cloud bow things that HARP2 will be doing for us. But it does allow you to get at aerosol microphysical and compositional properties. And in particular, it's a good match to OCI as we start to look at how aerosol absorption changes into the UV, where a lot of materials have rapidly increasing absorption, particularly dust and brown carbon. So the radiometric uncertainty expects 2% and polarimetric uncertainty of about 0.003. So accurate polarimetry and radiometry. And the spectral resolution for radiance is on the order of 2 nanometers. So pretty high spectral resolution. And we'll come to why the polarization is at a different resolution in a sec. You want to look at things from multiple view angles so you can see how these different phase functions vary. And then you really want the accuracy, particularly for looking at getting an adequately accurate aerosol optical thickness, real refractive index. And here we come to the modulated spectrum. So what they do, which is different from what HARP2 does, is you are modulating the spectrum with the polarization of the incoming light. So the depth of this modulation of the spectrum is determined by how polarized the light is that's coming in. And yeah, this got cut off. But basically you have the polarization multiplying by a cosine where the phase delay of the polarized radiance varies with wavelength, and that gives you this modulation. And that's why while the spectral resolution of the instrument is only about 2 nanometers, in order to look at how deep the modulation is, you need to have at least 1 full sinusoid to get the modulation depth. So does anybody have any questions about that modulation depth bit? So here it is again. This is just showing detector counts and wavelength. And depending, so this is a very strongly polarized scene. This is quite weakly polarized. And these modulations, the depth of the modulation is determined by the amount of polarization. So because you need to have a full wave to look at to get the modulation depth, the polarization is at a closer spectral resolution than the native spectrum itself. And it starts off at around 10 nanometers over here, and you can see it gets wider. It's out to like 25 nanometers at the red side of things.
I have a question.
Go ahead. Oh, should I go back?
If the spacing between the modulation gets bigger with wavelength, how do you balance like hitting that well and aliasing issues? Or is this not something that
No,
goes into that?
that so primarily the polarization in atmospheric windows is changing much more slowly than the modulation is changing. One of the places where aliasing is a concern is when you get into absorption bands, like the oxygen A band, where the A band is varying more rapidly than the modulation is, and so that can also potentially alias the degree of polarization signal in the oxygen A band. So they're going to try and do degree of linear polarization in that absorption feature, because the main reason being that if they can do it, then it has the potential to allow us to estimate cloud, not just cloud top thickness, not just cloud top height, but also cloud physical thickness. And the reason for that is the amount of absorption that you get from the top of the atmosphere to the top of the cloud is the same for the radiance and the polarized radiance. When you form the ratio of polarized radiance to total radiance, that's the degree of linear polarization. So the above cloud stuff cancels. And then all the scattering inside the cloud is what modifies the degree of linear polarization. And so if you can see how that changes in the oxygen A band, you can actually get an estimate of how many scattering events there are, and thereby the physical thickness of the cloud. So it's going to be, that's one of the things they don't promise to do, but they'd like to.
Okay, cool. Thank you.
Sure. And I'll pay you later for the question. Yeah, so and so what the SPEXOne has, they have 5 viewing angles, and then they split, for each viewing angle there are actually two measurements, one in parallel polarization and the other in perpendicular polarization, and they get split like this. So basically each one of these gets split into 2 parts of the focal plane array, and then to get the degree of polarization, you take the difference between them and divide by the sum of them, and that gives you this rapidly oscillating thing that you then demodulate. And so all 5 view angles and both parallel and perpendicular polarizations are on one focal plane, and this is showing the spectral variation. This is the cross-track coverage that they have, which is only about 100 kilometers. And then these are like I say, these are the 5 different viewing angles. So you've got viewing angle, spatial coverage, and spectrum all on one focal plane. And then this is just providing an example of what that kind of thing would look like when you're measuring the radiance. And these these two things are their measurements, and then this is the inferred radiance and degree of linear polarization. And yeah, they're doing okay there, although there's no quantification. So we had a really good calibration campaign with SPEXOne. They did a really nice calibration over in the Netherlands. But they don't actually have one of these Glamour or Circus or whatever you want to call it, laser facilities. And for spectrometer, having that kind of spectral calibration where you can actually know exactly what your spectrometer is doing is really, really helpful. So they spent the better part of a week in the lab with the laser system, scanning it a lot backwards and forwards and making sure that they didn't have out-of-band leaks and characterizing so that they can correct for any of the flaws that there may be in terms of stray light and scattering. So yeah, the main thing they were getting out of that was stray light correction. This you can do with broadband. They got this out of that. Field of view is also pretty helpful with the laser system, and this was broadband as well. And yeah, and so they always do a transformation to local meridional plane. And as I say, if you're looking at the data as a scientist, it's often better to transform to the scattering plane. This is the calibration setup at SRUN. I think I was there in 2019. It was the last time I was there. And so what they did was verified that they can get the degree of linear polarization really accurately. These are the errors. So they got errors of less than 0.0025 over this angular range. And then the only place where they start to get slightly bigger errors is where the glass plate angle is not particularly well controlled, where you have very, very high angles. So they reckon their accuracy right now is on the order of 0.0025 for the degree of linear polarization. And then the spectral calibration, this is the wavelength to pixel matching. And obviously this is a thing that's really nice to do with the laser system. And you can see there's a slight bit of, it's not perfectly linear with pixel. So you do need this calibration to map from pixel to wavelength. And then the retrieval scheme, which I mentioned before, you have the state vector, which is everything about the aerosol, forward model, and then match all those observations. And so what the SRUN has been doing is they've been testing the retrieval algorithm with simulated measurements where the assumptions that go into the simulation are not the same as the assumptions that go into the retrieval scheme, because the simulation comes from ECM, I think ECM 5, aerosol model, and general circulation models and aerosol models usually have, they'll have different species of aerosols that they're carrying as separate traces, and they'll have optical properties that go with each of those traces, and then you mix those things together and simulate that. Whereas typically the remote sensing retrieval schemes, you have an accumulation mode, a coarse mode, and then you retrieve the refractive index of each one and the amount of each one. So the assumptions are somewhat different. And they've applied that retrieval algorithm to the synthetic measurements to test how well it's going to work even under the relatively harsh conditions of not having the same assumptions. And so they got pretty good results, actually. This is sort of a scatter plot thing, which is in the eye of the beholder. But what I've like is these figures where they have the retrieval minus the truth divided by this standard deviation. And that's for a normal distribution, it should fit within these dashed lines. So they have a small bias in the optical depth, almost no bias in the single scatter albedo, and actually they are overestimating their errors in single scatter albedo. This should be more peaked. So they're doing better than they thought they would. And then this is obviously showing us something of a bias in the effective radius, small bias in real refractive index. So pretty nice results from that. And then the airborne campaign in 2017, that instrument had 9 view angles. Spectral range is a little narrower in the UV, slightly longer infrared, but it's not really, because this was unusable as they got further out in the infrared because it was second order in the spectrometer. Oh, look at that. Lovely graphic. I'm hiding there. And this is Martijn Schmidt, who is one of the instrument scientists. He's the Dutch person I've met who really likes surfing the most. Whenever there was a down day, he was off to the beach like a shot. It was really impressive. I mean, we were getting up early for the ER2 because you have to be in around 5:30, 6 a.m. Surfing days, he was gone by 4 a.m. So there you go. And here's all the data we got. There's some really nice underpasses of Calypso, these long legs on a diagonal, Calypso underpasses where we could use the HSRL LiDAR to calibrate the Calliope LiDAR. And that's also nice for us that we have Calliope overhead and also the other Aqua, Modus Aqua, and the A-Train. And then this is just comparing the Specs instrument to my instrument. We got really nice agreements. Good aerosol retrievals validated against AeroNet. And there's, yeah, I shouldn't have done them. And then a good comparison to HSRL2. The comparison is probably not as clean as they would have liked. There were certain issues with HSRL2 during this campaign where we had these really spectacular wave breaking in the stratosphere where the ER2 was pitching and rolling, and there was a lot of turbulence in the upper atmosphere, and the turbulence caused some issues for the LiDAR. I think they had issues with speckles caused by the turbulence in the upper atmosphere that made the HSRL capability difficult to use. And then forest fires in Arizona, there's some nice results that Vanderlei and Lorraine's group have got on doing remote sensing of the forest fires. This is just showing the SPECS results against HSRL2. This was a fire over the Grand Canyon, which was pretty spectacular. This is from the pilot took these pictures from the ER2 at 20 kilometers altitude. And then there's a considerable synergy between SPEXOne and OCI and HARP2. SPEXOne has a much narrower swath, but it is expected to be a really accurate polarimeter that goes down into the UV to 385 nanometers. And so that's quite a bit shorter than we'll get with HARP2. And so for characterizing absorbing aerosols, that's going to have a lot of benefits. You know, HARP2 obviously has the hyperangular thing going on and also a broad swath that matches up to OCI better than SPEXOne. And that's it. And it's 5. All right. So any questions? Go ahead.
Yes, so I have one question about the bias that you found between the retrievals and the simulation. So when you found those bias, how do you correct them? Or you just
I think right now they're going to redo that. So that was the previous version of the retrieval algorithm. And so what they're doing right now is they have an updated version, and they're running that algorithm on the synthetic data now to see whether they've got rid of the bias or not. It's actually a pretty small bias. It's 0.01 micron in the accumulation mode, and you know, if it was most instruments, you'd be really, really, really happy if you got within 0.01 micron. That's a tiny bias. But there's no reason why they shouldn't be able to correct the bias, because 0.01 micron is actually makes a significant difference in the polarization at side scattering angles, particularly in the near infrared, like at 750 nanometers. That actually makes a fairly substantial difference, because the small particles are right in the transition between being Rayleigh-like and sort of moving up that curve and becoming more me-scatterers where they depolarize. So you have a really rapid change in polarization and a considerable sensitivity there. Yes?
You since mentioned that X is really for aerosol. Is there anything for like clouds from elements? And then a follow-up question is, any of this data going into all going to be for like speculation, or it's just characterization?
I didn't. Did you say? Could you say your last sentence? I didn't quite hear the.
Will the data be considered or used for like atmospheric corrections or tweaking the atmospheric corrections? Like,
Yeah. So clouds. It's not going to be as good for doing cloud bows. It's not going to see cloud bows very often. So not as good for doing droplet size distribution. However, because it has the A band, and the A band will be good for the total radiance, and it has 5 view angles. OCI has an A band measurement, but only the 1 view angle. So what OCI is going to get is going to get a cloud top pressure. What you get with the 5 view angles, if you do the calculate the weighting functions that I showed for the different viewing angles, the high view angles, the weighting is much closer to cloud top, and the nadir angles, the weighting is pretty much all the way through the cloud by the time you get close to the edge of the A band. And what that means is by combining those 5 angles, we should be able to do a cloud physical thickness. And the main reason that you want to do a cloud physical thickness is because that allows you to estimate the number concentration of droplets in the cloud without assuming that you have an adiabatic liquid water content profile. The existing cloud number droplet products that are used are almost invariably strictly for low clouds, and must assume that the profile of liquid water is adiabatic, that the liquid water content increases linearly with height, that you know what that condensation rate is, and then you can use the optical depth and the effective radius to infer physical thickness and droplet number. If you can actually retrieve the physical thickness, that makes me a lot more comfortable, primarily because biases in droplet sizes from remote sensing retrievals using the Nakajima-King or bispectral algorithm generally depends significant on the macrostructure of the clouds. And the macrostructure of the clouds tends to change as the number concentration of droplets changes. So when you transition from an overcast stratocumulus cloud deck to a broken cell cloud deck as you move up the trade winds, that transition is usually associated with a dramatic decrease in droplet number concentration and an increase in droplet size. Because of the way in which the bispectral scheme works, when you start having puffy clouds, any light that leaks out the side looks like light has been absorbed. Right? If it doesn't come back to you, you think it got absorbed, it had just happened to leak out the sides. That erroneous absorption gives you a bias in your droplet size retrievals that is high. So you get a high bias in droplet size. And then the number concentration using this adiabatic business is to the reciprocal 2.5 power. So you amplify any errors in your effective radius. And it's exactly in that regime where you want to know whether it's a macrostructure changing cloud or a microstructure changing cloud. So yeah, the SPEXOne cloud physical thickness thing does have the potential to be really beneficial in understanding the differences between errors and changes in microstructure. Yeah.
You mentioned the multiple angles that SPEXOne measures as handy for the distribution, the shape of the scattering distribution. What I'm wondering about, I think there's a picture, and it might be just because of the cartoon, but due to how far the satellite is away, the angles look like they would sample very far away scenes. So I'm wondering how, if you're wondering what to really, how to picture that, if that question makes sense.
Yeah, so what's, I guess there are two pieces that I see to it. The PACE satellite will actually be steering itself as it flies along, because what you want to be able to do is, so you've got your 5 view angles, right? I only have 2 arms. So there's 2 arms and my legs, right? So you're flying along and you're not actually seeing everything simultaneously. So you have to stick it together. If the PACE satellite was not your steering, these guys would never see the same real estate as this guy. But we actually yaw steer the satellite so that we co-register this and this and this all to the same point on the ground. So we see the same point on the ground from all 5 view angles.
But that's separated in time.
Separated in time, yeah. And all of these instruments, the multi-angle looks are separated in time. That's true of HARP2 as well. HARP2 will benefit from the yaw steering. HARP2 didn't need the yaw steering because its swath is so wide that if we didn't yaw steer, they'd lose a couple of 100 kilometers either side of the swath, but they would have been able to co-register the vast majority of their pixels because it's a very wide swath instrument.
But now I'm wondering, when a farther angle aligns with the point that another angle was looking at previously, then what's the difference between the 2 collections?
Could you repeat that? I didn't quite hear the...
Yeah, so you're saying if you have your arms spread out multiple angles, if there's a point, the swaths would sample that same point, correct?
Yes.
And so then why does that even become different? If they're looking at the same point, how is that a different angle after the...
Oh, so, okay, so I'm doing this. You're going to get me dancing, aren't you?
Yeah.
So you've got these, and what you're trying to do is get all of those registered to the same point. So they're all looking at the same point, but the viewing angle that they have when they look at that point is different. And so,
Okay, thank you. I see.
so what that gives you, let's not bother with that, is so you have those phase functions, right, that are all looking different. And rather than just having one view where you only have the one view of the one phase function, you now have 5 scattered across that phase function, and you can differentiate between, say, dust and sulfate. Sulfate's a spherical, dust is not. And the angular scattering patterns are different. And so you have those 5 angles.